All right. So first of all, before we kind of go through the slides and I point out what's most important, let me just give you a little bit of background on what the final roughly will be like. There'll be 10 questions as usual. I'll probably set the time limit at like 3 hours. It's designed to take 1 hour. So kind of a normal, typical exam. Face-to-face, usually the exams would be a 2 hour time block, but I would still design the exam to take 1 hour. So like I said, 10 questions. It will probably be at least half programming, maybe even a little bit more. The programming questions will come in the form of write stuff yourself, or me showing you code and asking you what this code does. For questions like that, I'm not asking you to tell me on a per line basis what this does. I'm asking you to follow the code and ultimately tell me what this code accomplishes. Like if I gave you a simplified example, this wouldn't be something that would necessarily be on there. But like I said, like could be, so because I mean, the exam is also going to cover just C programming and pointers and things like that. But, let's say I had a function that took a string as a parameter, a char pointer, and it built a new string that was the original string in reverse or something like that. Well, there's going to be a lot of lines of code in there where you're creating memory for a new array and going through a for loop and things like that. And I'm not looking for you to say this line makes a new array. This line sets a for loop where you have a counter that goes, sets up an I, something like that. I want you to effectively trace through the code by hand and then tell me in the end, oh, this code effectively reverses a string. That's what I'm looking for as the result to a question where I give you code and say, what does this do? I could also have some given, some code where I say there's a function that already does X, Y, and Z. Write some code that takes advantage of that function to solve some other problem, something like that. So some drill-based computer programming questions that basically maybe test your knowledge of C, your comfort level with C, working with pointers, that kind of stuff. The exam I'll have up by midnight on Sunday. It might be up earlier than that, but I'll promise it'll be up by midnight Sunday. I just need you to do it before midnight on Friday. You do need to complete it all in a single sitting. It is closed note, closed book, closed neighbor, closed internet. I want to see what's in your own head. So with that in mind, I'm not, taking off points for small little syntax errors and things like that, things that a compiler would catch, because I'm not necessarily expecting you to test your code in a compiler. If you want to use a text editor that will help you format your code a little bit or something like that, that's fine. You can. But, again, the expectation is you would just be typing in the code in something that, should look a lot like C, something along those lines. So you'll have 3 hours to take it. You need to do it all in a single sitting, close book, close note, close neighbor, close internet. I just need it turned in sometime before midnight on Friday so I can get it graded over the weekend, to get grades turned in on the following Tuesday. If you do turn it in earlier than that, there's a pretty good chance I'll be grading during the week. So you might get your grade back, but you wouldn't see you might not see the feedback, because I don't think the feedback gets released until all attempts are graded. I'm not positive on that. Blackboard's a little bit weird on that. I need to think about whether what I just said is even true. I might not grade them early, actually, because the way I like to grade exams, I turn the names off and I grade them all one question at a time. So I'd rather have all the classes question 1 in a row, all of it in question 2, so on and so forth. So I actually probably would wait until Saturday morning to actually grade them, with that in mind. So with that in mind, you'd actually get your feedback and stuff back probably sometime over the weekend. All right, so questions about the exam in general. Okay, anything specific that we've done more recently or something like that that you want me to cover? And I'll ask that question again here in a little bit, but I was going to go through the slides and kind of point out things that I think are important to know and things that are maybe less important to know for the exam. Remember, the policy of my classes are if you did poorly in the midterm and you do better on the final, I'll replace what your midterm exam score with whatever you got on the final. I do anticipate the final being a more difficult test than the midterm, given that it is more programming. But you know, again, the types of questions, the types of programming questions I would ask on an exam maybe will tend to be a little bit more generic than, you know, things that, you know, you might spend 5 or 6 hours on in a homework assignment or something like that. So I'll try to mix things in with like fork system calls and things like that. I might also kind of set you up with like shared memory or something, or give you a starting point for some stuff just for the sake of time. I also don't want you to necessarily have to go and memorize a bunch of stuff. So anything that wouldn't be just generic C, I might give you like a sample starting point for, because I'm not necessarily testing your ability to, you know, effectively copy 6 lines of code that you would do to set up shared memory or something like that. I really want to just see, are you able to problem solve with that kind of stuff? Because I mean, I know you can take an example program and set up the 3 or 4 lines to get a shared key and create your shared memory and that kind of stuff. So I'm not concerned about your ability to memorize that. So I wouldn't waste your time on that. I would consider the understanding what those different tools are used for. All right, so before I start flipping through the slides, are there any questions that you want me to answer or go over?
We can probably go over this more near the end, but I am still a little confused about when we do create a fork and if it's in a loop, if the fork keeps going, where it jumps back to in terms of if it's in main, if it jumps outside of the loop, or what that looks like.
Okay, well, let's actually look at that now. And let's see, do I still have that? Well, here, let me. I didn't actually reboot this, but since we won't run it, I can answer your question by just showing a picture of one of the, so showing some code. So this is the guy. So the idea here, so she's asking about the fork system call. So this guy right here, what this guy right here does is he creates a duplicate process. Okay, and I think you understand that because your question seemed to indicate, where does it start? All right, so it creates a duplicate process, and that duplicate process, well, whether you're the original parent or you're the child, you start your adventure right here. You don't reset the program. You don't go back to the top of main. You literally came into existence right here and pick up from here, which means that if you were in the inside of a loop like this guy, so while begin not equal to end, and you were born, you were the child, let's say, that was born right inside here, you pick up right here, you'll hit the end of the loop, you'll spin back up, and you're still inside this loop. And you're going to ask the question about your begin relative to your end, if those values happen to change in there. Okay, so that's as opposed to maybe an assumption you might say, oh, well, this creates a duplicate. Does the child start up here at line 1 of main? It does not. So when you call fork, that new process as well as the old process go to the very next line. And that's why we're asking the question, who am I? If I'm the child, do this crap. Otherwise, that must be the parent, do this crap. All right. So you literally pick up on the line immediately following that fork call. And that's where you go. Does that answer what you're asking, or is there more to it?
So what you just mentioned now with fork, that just creates an off-split child. It's not like it creates a new parent plus a new child, right?
Correct.
Like,
Correct. Yeah. So when you get to this line right here, two things exist. The original, so not a new original. So yeah, a new parent does not come into existence. It's the original dude and then a brand new child. That is a duplicate of the parent's memory. Yeah, so what used to be one process now is two total processes, the original plus one new one. All right, anything else regarding fork?
I think that makes sense. Thank you.
Yeah, so really the challenge there is that fork is actually pretty simple unless you try to overthink it. Because it makes perfect sense, you might say, because like we were dealing with like a thread in Java. We spawn off a thread and that thread goes off and just does its own little function inside of like run or something like that. Where fork is a little bit, like this fork, the next line of code is line 85. Whereas this fork, the next line of code is 97. So it literally just picks up from that point in time. You've just kind of created a quick clone that exists as like a snapshot of the parent right at that exact moment. Whatever the parent's current values were for begin and end and all that jazz, it just duplicates it and picks up from there.
And fork creates a process, not a thread, right?
Correct. Fork would be the predecessor to multi-threading. It's not necessarily worse than multi-threading, because fork does create a full secondary process that gets all the rights and privileges on the operating system as any other process gets. It means it gets its own time on the CPU. It has its own memory associated with it, its own everything. It's a full, the parent kicks the bucket, that child process is still alive. Whereas if you had a program that was multi-threaded and the parent spawned off 5 threads and then the parent was killed off, those threads would die too, because the threads are sharing the parent's resources. Fork does not create threads. Fork creates brand new processes that as soon as they're born, they're standalone. They're owned by the operating system, not owned by the parent. Hence the inter-process communication stuff, where we need to be able to communicate between our different processes, whether or not we're talking to our parent or we're talking to a sibling, potentially. All right, so anything else ahead of going through the slides? You can always ask more later as well, but I want to cover the things that are known problems ahead of time. Okay, so I would maybe just blanketly say, I'll kind of skirt through some of the early code, early slides, and kind of say whether or not I think they're going to be important on the final. But like I said, the final will be primarily from stuff since midterm. I would say if there was a global theme that you should kind of be familiar with, is the different types of inter-process communication we've discussed and when you might use those different things. All right, again, if I want you to do something with a semaphore or with a signal or with shared memory, I'll give you the code as a starting point for that. So I don't want you to waste your time memorizing those 2 or 3 lines for setting something up. I want you to more think about it like, okay, I went to Home Depot, I have this semaphore tool. When would I use this tool? Same thing with shared memory, same thing with signals, that kind of stuff. All right, so that might be a theme of this final exam, is how do processes talk to each other? All right, so let's kind of skirt through some of these things. I'll kind of flip through pretty quick, and I'll only stop if there's something that I think you should definitely refocus on. you should definitely still be familiar with structs, whether it's I give you some sample code that has uses a struct or something like that. I can't imagine I'd ask you to write a program where you have to come up with a struct on your own, more so for the reason that maybe is a little bit more complex and I want to test you on in an exam situation. But if I did have some code where there was a struct, what's a struct? It's effectively like a Python dictionary. It's effectively like a class that only has name value pairs and no methods. That's what a struct is. So nothing super special, but you should know what those guys are. And if you see one in the wild, not be completely oblivious. Definitely be familiar with pointers. So know the syntax, know what star something means, know what the ampersand means for getting the address of something. Know that arrays are, have a base address and things are offset from there. Should be comfortable working with memory. Specifically, I probably will not ask anything about the Linux driver stuff that we did in the first 8 weeks. I'll focus on the interprocess communication stuff. So you don't have to go back and review like the insmod and that kind of stuff. But some of the things we looked at early on with like structs and pointers, those are things I'm going to assume you're comfortable with now, but not necessarily in the context of the microkernel or communication between kernel space and user space. I would say kernel space and user space, I mean, it's something you should know exists, but it hasn't been a theme since the midterm, because now we're just thinking about two running processes that are running in the operating system trying to talk to each other. Not necessarily bridging between something that's running in the kernel, like a module, talking to a process that's running in user space, and how does that cross communication work? So I wouldn't really focus on that at all for the final. The final is going to be much more of the processes talking to processes, normal processes talking to normal processes, not special kernel processes talking to normal processes. All right, so definitely understand the concept of an atomic operation. I think this actually was something we talked about just before the midterm, or leading up to it. But that's kind of where our idea of semaphores comes in. Atomic operations are operations that occur as if they're occurring in a single CPU cycle. If an operation is not atomic, there's an opportunity for something to occur in the middle of an operation. And we kind of saw that last class when we saw our output of our multi-process merge sort, where we had some of our children actually getting the, finally getting the opportunity to write out to the screen later than the final parent who finally did the sort. So we actually had, I think, our sorted output displayed 3 or 4 lines earlier than some of the children finally finished spitting out their answers. Like, oh, I'm working with this portion, something like that. So it was clear that the communication, the signals had already been sent, but the access to the IO subsystem hadn't been allowed. The children were still waiting in line to get that stuff spit out to the screen. So that would be an example of situations that aren't necessarily happening atomically and create this idea of a race condition where you might have, for instance, 2 child processes both trying to get time on the IO subsystem, and ultimately we don't have any guarantee on what order they get that without a power tool like a semaphore that allows somebody to grab something and then locks other people out. Realistically, operating systems IO subsystem is probably using semaphores to at least make sure that two processes aren't both getting IO time at the same time. But we don't necessarily get to control order with that either. So this is kind of our transition when we started talking about fork. I don't think I'll ask anything on the exam about file locking. That's almost like a predecessor to our real interprocess communication stuff. So I would focus more on the idea of the use of semaphores, the use of shared memory, and the use of signals. Those kind of three go-to moves. And we'll get to it here in a few minutes, our bulletin board thing with shared pipes. Well, we'll talk about it here in a few minutes. I probably wouldn't have you do anything with implementation of that either, but there could be a question related to that. Well, so I'll get back to that later. But I don't think anything with file locking would be of interest. This concept of blocking versus non-blocking code, though, being, so this is kind of the rationale for why the fork system call even exists, right? We have, we have something we want to get done, but we have something else that also needs to get done. And these two aren't necessarily directly related to each other, or at the very least, they're not dependent on each other. So it might be nice for us to do those things relatively simultaneously at the mercy of how many processor cores we had on the computer. So if we can create a child process to go perform a secondary task, allowing the parent process to continue on and not block the child process from doing their portion, that might be handy. So this blocking versus non-blocking code, a blocking code would be code that does not allow you to get to the next line until after it's completed. Whereas non-blocking code would say, this guy does something, but for instance, a new process was born and both the new and the original process get to the very next line and are continuing on parallel but different paths. So this is that file lock example. Like I said, I don't think I'm going to ask you anything about file locking. It's kind of like the primitive predecessor to real interprocess communication. There'll certainly be at least one conversion question on there, probably just one conversion question, but if I get desperate for an extra question, I might put another one on there. Just as a reminder from the midterm, I like sometimes giving you a conversion question that takes advantage of that knowledge of why we use octal and hexadecimal along with binary. That idea that the entire octet system can be represented in 3 bits, 000 all the way up to 111, and the entire hextet system can be represented in 4 bits, 0000 to 1111. Which means if I ask you to convert something from hexadecimal to binary, for example, it's actually pretty easy as long as you recognize that trick where you can turn any hextet 0 through 9, A through F into its 4-bit equivalent and get the binary version of a hexadecimal value pretty easily, as opposed to going through the long-winded process of turning, a hexadecimal number into decimal and then a decimal number into binary. You'll ultimately get the same answer. Your same final answer will be right, just your path will be a little bit less obnoxious, I guess. So be on the lookout for those base conversions. But if I tell you to go from base 7 to base 13 or something like that, well, then that's out the window. You'll have to do the the longer winded way. I probably wouldn't ask the question specifically about ROT 13. That was just a sample of kind of, I think we did that with what, shared memory or something like that. Yeah. So definitely shared memory, understand the concept of this, be able to work with shared memory, which really isn't any different than working with any other like array or variable, because I would probably give you the couple of lines to generate the shared memory, because I don't want you to spend time memorizing that. But regardless, understand the purpose of shared memory is to create an area in memory that lives outside of a given process, where multiple processes can all access that same memory, as opposed to a copy of that memory. So that's a form of inter-process communication. Something like this could be, represented somewhere, the difference between a void pointer and a char pointer. And this has to do with when you're doing pointer math, like here v plus 3, if it's a void pointer, that's going to be whatever the size of a memory address is on that computer. So let's just say it's a 64-bit operating system. Maybe this is 8 bytes. So this void pointer, when I say something plus 3, this will be the base address plus 3 times 8, which is 24. That's what it'll give you, because you're taking 8-byte steps since it's a void pointer. Whereas if something was a char pointer and you add 3 to it, you're only taking this base address and you're adding 3 to it, because the size of a char is 1 byte. Okay, so C is a strongly typed language, so the type of pointer we have does dictate how big of a step we take when we're doing pointer math. All right, so the message passing was like the bulletin board thing we talked about last time with message queues. I probably will not ask a question, certainly not a programming question, about message queues. We did have a sample thing. If you remember, message queues kind of work as a central, it's like shared memory.
Damn.
What was the question? Or just random screaming? So remember that message queues work with, they're effectively shared memory clustered together into a collection of queues, where those different queues have like bucket numbers. But when you read something from one of those message queues, it gets removed from the queue. All right, so that means if you have one process read from a message queue and another process write, well, you have a process write to a message queue, and then you have 2 other processes that are interested in that queue, only the first one that tries to read from it will get that next value, because when they read from it, that value gets removed. And that is a different behavior than shared memory, where if you have a parent process that puts something in shared memory, both children, for example, would both have access to that value in shared memory whenever they needed it, as long as that value didn't change. But reading a value from shared memory does not remove it from that place in shared memory, whereas reading a value from a message queue does actually remove it from that message queue. So the punchline there would be message queues kind of dictate, they're only a very good tool for very specific types of communication between processes, where shared memory is maybe a little bit more flexible because it doesn't dictate as much about how it works, and really just allows you to work with normal plain Jane variables that just happen to live outside of the memory space linked to an individual process. All right, so semaphores, remember these guys are kind of like special kinds of integers, where we use them to protect a resource. And really a resource is typically thought of as this section of code known as the critical section. And that section of code, maybe it's one line, maybe it's 30 lines of code, but effectively you have a bouncer that lives at the door, and that's the semaphore. And even if you have multiple processes that all want to enter the same resource at the same time, they have to get through the bouncer, and that semaphore, that bouncer, is able to move atomically, is able to make decisions atomically, which means that, you know, two different processes can't start talking to the bouncer, then one of them squeezes by while the bouncer was still making a decision. It happens atomically and will lock other processes out when they'll have to go back and check the door again in some period of time. Maybe they go to sleep for 2 seconds or something like that, and then check again to see if it's available, you know, whatever it is. But a semaphore is a integer that increments and decrements atomically. And if you have 3 resources available to you, you can have a semaphore that is a counting semaphore where it'll count up and down, up to 3 and down to 0. Actually, it would probably count up to 2 and down to 0 for 3 resources. Actually, no, it would count up to 3 because 0 would mean they're all available. And then 1, 2, 3 would mean they're all taken. Or you can have a binary semaphore, which just says, hey, look, we got one place, one part of critical code here, and we're going to either let it's either available or it's not available. And that's the same thing as a counting semaphore, it just only goes up to 1. So there's not a difference between them other than the assumption of whether we're protecting the number of things that can access a number of resources, or there's just a single resource that we're locking down. All right, but the overriding use of this tool for semaphores is the idea of atomic operations and protecting a section of code so that no more than one process can access that section of code at the same time. And typically that section of code would be, you know, if we're using the fork system call, for example, you know, we kind of go back over here. Let's say that inside of here and here, we were doing some file IO, reading and writing from a file or something, or let's say writing to a file, making a change to a file. Well, we wouldn't want the child and the parent to both be changing a file at the same time. So what we might do is maybe we have a function that is the function we want to call, and that function, and that's the one that makes the changes. We would protect calling that function behind a semaphore. And if the child tried to grab that resource when the parent already had it, the child would be pushed away by the bouncer and then would probably have to wait for, you know, maybe the child would wait for 3 seconds or something like that, or 1 second, whatever, and then spin back through a loop and try again. And only after they've gotten into that critical section can they break out of that loop and keep going. All right, so sometimes we want to protect a resource like a file when more than one process might change a file, and you're at the mercy of whoever wrote last. And if you don't want to have to deal with whoever wrote last, you want to make sure that anybody who opens the file for writing finishes their writing before another process can open that file for writing. All right, so that's our semaphores. So here's our binary and our counting semaphores, basically the same thing. One's just 0 or 1, the other one goes up to some number. Again, if I wanted to use semaphores, I would give you some sample code for your starting point, or I would give you, maybe I would say a function exists that will hand you the integer, the special semaphore integer or whatever. So you can just assume that you can call upon a guy to give you the semaphore that you can then use. Similarly, you know, shared memory might be the same thing. So instead of giving you the code, I might just say there's a function that, you know, you pass the number 42 and it will give you the shared memory associated with that ID. Okay, so I just used the file IO example, but here's a shared memory example with semaphores where you have a central place in memory that all the child processes might have access to. because you have, if they all have access to that shared memory, but you still might want to control who can change that memory at once. That way you don't have this situation where maybe process A wants to change it first and process B actually beats them to the punch and changes it. So you can use semaphores to control who gets access to that shared memory and when. All right, we already talked about the fork system call. Remember that the fork system call does return an integer. That integer that it returns will be 0 if you're the child process. It'll be something other than 0, which is the process ID of the parent, if it is the original. So this says, if I'm the clone, I'm the child, PID would be 0. Otherwise, I must be the parent.
I have a question about that.
Sure.
So, isn't it that, like, if you're the parent, you receive the ID of the child? Like, the ID you receive is not a parent ID, but a child ID?
Yeah, it's that.
Okay.
So the PID for this, if you're the parent, would be not the parent's own ID. It would be the ID of the child they just created.
Okay, got it.
Child. I think I did misspeak a second ago. Yeah, and it says it right here, what it actually returns. But remember, we also have actually a parent. That would be the parent's only opportunity right here to know about their new child. Because a parent doesn't have a function that allows them to get the process ID of their child, because a parent could have multiple children. So the only place that their new child has, they have the process ID of their newly formed child would be right here, which is why in one of our examples, we had an array of PIDs. So a parent can keep track of all their children because they're probably overwriting this variable each time they create a new child. All right. All right, so we initially looked at signals from the perspective of maybe exception handling, where, and that's kind of that the concept of using the raise system call. So we talked about raise versus kill. I would say that's an important concept, knowing those two things. They both deal with signals, but raise is how a process sends something to itself. So it's kind of like raising an exception, catching, throwing an exception, if you want to use Java speak. It just so happens that an exception in C, we're calling it a signal. We're screaming about something. So we can either use one of the built-in standardized signals. We're writing our own handler, so it doesn't necessarily matter which one we use. Or we can use the user-defined one, user1, user2. But regardless, when we use the raise system call, we are letting this process, we're letting ourselves know about something and probably having it connect to some handler. I mean, nothing says you can't raise a signal to yourself, even if you don't have a handler. Although I thought we experimented with it. That might block. I don't remember. Doesn't matter. I'm not asking you about that. Like behavior under weird circumstances, it would be typically you would say, you know what? I'm interested in a SIGINT. I have a handler for a SIGINT. So if I raise SIGINT, I'm effectively saying I want to call my own handler. As opposed to the kill command, which is our inter-process communication tool, which allows us to send to a target a process ID, is the way we looked at it. You can also send it to a group, which we did not look at, where you can have a whole bunch of processes all belonging to the same club. And then in order to reach out to all of them, you can actually send it to a process ID group. You don't have to worry about that. We didn't talk about that. We just talked about targeted kill commands where we send a very specific process ID, a very specific signal, which would then trigger that process ID's handler for that signal. So do understand the difference between raise and kill. This slide. Also know how pause plays a role here, where if you have a process that is, kind of at a holding point right now, it needs to wait for something else to occur, you can tell that process to pause, saying, look, you can't continue on right now, a la here's our merge sort, where we said, look, I'm the parent, I've already created 2 kids, now I have to wait for my kids to finish. This parent couldn't go on anymore, so this actually goes back to our concept of blocking versus non-blocking slide, where this parent is purposely blocking. They're saying, I cannot continue right now. I need to wait for my kids to finish their job. So they're going to sit, pause, and wait for a signal. I just happened to register the parent with the signal they were interested in right beforehand, but that doesn't have to happen. As long as the current process is registered to be interested in this signal, they would be able to handle it. All pause says is wait here until somebody screams at you. And this scream would come from somebody else's kill command as opposed to a raise, because raise is only used to send yourself a signal and you're currently blocked. So effectively it says wait for a kill command to raise one of your handlers, or to target one of your handlers. Okay. And I don't really know how I would ask a question specifically about this. I suppose it would be fair game, maybe for a kind of a little bit more of an essay type question. We talked about at the end of last class, this idea of distributed operating systems. Kind of that, when would you actually, like merge sort doesn't exist to just be this torture treatment thing. Merge sort is an interesting problem because we can see the inefficiencies of merge sort in one scenario, where we can see the great efficiencies of merge sort in a different scenario. We explored it recently through this multiple process concept, which as long as you have multiple cores, we're gaining some real efficiencies by working with the different parts of the array separately, simultaneously. But we can certainly see how that would even increase for really, really, really large data sets across multiple computers all over the internet, especially as our internet connection speeds get faster and faster and faster, where we don't have this drastic speed difference between, if we're on our computer and we're saving a file to our hard drive, and our hard drive's a solid state hard drive, that file saves very quickly. Instead, if we're using the cloud and we're saving a file on the internet, and our connection to that hard drive is our cable modem internet connection or whatever, while that keeps getting faster and faster and faster, that communication channel, it's still slower than our communication channel with our local solid state hard drive. But at some point, as that speed increases and gets faster and faster and faster, and we're already way closer to that than we were years ago, we're at the point now that in terms of practically syncing stuff with the cloud, it's effectively real time because it's happening passively in the background, like using Dropbox or Google Drive, something like that, where it just makes sure that the cloud stays synced up with whatever you have locally. But as that becomes faster and faster and faster, and we're able to have data shared across multiple physical computers, all of a sudden this current limitation of how many cores can we fit on a single processor goes away. And now we're just at we're at a situation of how many cores can we have work on the same problem across 1 million different computers. If you have 1 million computers, each running 4 cores, you have 4 million worker bees, 4 million things you can do simultaneously. And now you start opening up the power of, for instance, like something like merge sort, which is a divide and conquer type of algorithm, where you can have some gigantic data set that you want to sort, for our example here, and have 4 million workers work on different portions of that data set. And all of a sudden it gets sorted way more quickly than it would if you used like a local insertion sort or something like that. So this idea of distributed operating systems is something to kind of look forward to. At some point in the future, we're already starting to, dip our feet into this as we, we do see a lot of these different ecosystems like, Xbox Live and stuff like that, that effectively are distributed operating systems where you have multiple people that come together that have communication channels and they're streaming type stuff. And that's just going to become more and more relevant as our internet connection speeds keep getting faster and faster and faster. And our compression algorithms keep getting better and better and better. And those two things relate to each other, right? If your internet connection speed is of speed 100, whatever, just 100 units, let's say, well, if you can compress stuff twice as good, you've now increased your connection speed by 100% without actually making it any faster, because all your data is now half the size because you're compressing it. So we have lots of kind of strategies for increasing the speed of things over different communication channels. One is through compression, another one is just making the channel faster. Thirdly, you can just say, let's compress it and make it faster. Keeps going in that direction. Okay, so questions about any of that stuff? I think that probably covers the stuff. Hopefully this final conversation like this kind of pulls together all the different pieces throughout the semester and kind of sees how they all ultimately link back to each other and why they all have to exist, even though they were individually in like these weird pod segments. Like, okay, well, why would I ever need this? All right, so anything else you want me to cover, answer, yada, yada, yada? Okay, like I said, the exam will be up by midnight on Sunday, probably before, but I promise it by then. And I just need you to do it in a single sitting sometime before midnight on Friday. All right, questions, comments, concerns, bribes? All right, I will see you when I see you.
Thank you.
Yep, later.
Thanks, Lemon.